how I'm just curious to know about the way that other of your profs are using Zoom or technology. I mean, is there someone who I'm just wondering if there's anything that I can improve, like in terms of the way that I'm writing on this document versus like writing on the board and having a camera that's zoomed out. Do you have any like experience with something else that works really well, or does this work better than the other ways?
I've had a few profs do different things, and I think this works the best. Like writing on a tablet, and then just us looking at the tablet writing. Like I had one prof who had like an overhead on a piece of
Yes.
paper, and I didn't like that honestly very much at all because like the pen doesn't show up as well as digital pen. You know what I mean?
Okay. And what about like writing on a whiteboard or something with a camera shot that includes the person and the board?
So I had the same prof try the same thing, and it was okay, but his camera wasn't good enough. So if your camera is like pretty good, then it's probably fine. Like I didn't mind it, but the fact was that I couldn't really read his writing because it was just blurry because the camera couldn't resolve it.
Oh, okay.
In my experience, even if the prof has like a really good camera, the problem is bitrate. That if the students don't all have great internet connections, there's a lot less information density in like a digital drawing. And so Zoom can compress it way more easily than it can compress an actual picture.
Oh, I see. Yeah, that makes sense. So you're saying that when I write on the tablet, it comes out crystal clear, whereas who knows what will happen to a photo?
Exactly. And even if like internet connection drops a bit, it's still much more legible.
I see. Okay. And what about what's your opinion? I would like to know everyone's opinion about this issue, which is attendance, right? So there's people attending without their video on. And what do you think about that? Do you think that no one should really care about it and everyone should be left on their own? Or do you think that attendance means that they should show their face?
Do you mean like if attendance is worth marks, like for?
No, I just mean that, you know, like when you're attending a class, right? I mean, everyone, if you're there, then you're visible in a way, so that it's, you know, I get to know people's faces and also they get to know each other, because, you know, you're supposed to have you're supposed to have your cohort, and you're supposed to recognize each other, right? So that in the future, one day you'll, I don't know, help each other somehow. I'm not quite sure how it works, but there's some kind of network effects, right? But if you're all individuals and you're all invisible, then you don't get any network effect. There's no point in going to university, right? Any opinions about this?
I think it's a sensitive issue. I totally agree with you, but like at the same time, speaking as someone who's like running tutorials for a first year class, it's like there are 900 students in the whole thing for first year calculus, and it's like so many of them have like there's like this broad distribution of situations personally where it's like asking them to have cameras on in their homes where we're all trapped is like it crosses some boundaries when you have that many students. So in principle, it's a wonderful idea, and especially for like graduate classes.
And so, like that, sure. I mean, it's not that I'm not sympathetic to their whatever their home situation is, but couldn't you? I mean, I feel like even if I was living in living with my parents with people screaming and so on, I would still like set myself up in a corner and try to attend so that I would be present. You know what I mean? But you think that even that is not necessarily appropriate to assume that they can do that.
I just know that some people are super uncomfortable with it. Yeah, and like it might not just be discomfort simpliciter. It might be like discomfort compounded with some kind of more general anxiety and especially with as you're saying, you lack the cohesion of your cohort when we're sort of isolated in this way. But I think that then that creates like an anxious positive feedback loop, right?
Right.
Where you're not integrated, and so turning on your camera is
So
participating.
you're
in
basically
something.
like, these people are all strangers in a sense, and
Yeah, yeah. So it's just,
what were you going to say?
I was just gonna say, I do agree that for many students, like, I mean, if you're going to school in person, it would be the same thing as turning on the camera. However, I do have, like, for example, in one of my tutorials, there's this one guy who, well, I have one tutorial that no one turns on the camera. And I remember asking about it, trying to, tell them things. But for many of them, it's like 5 a.m. or like, even 12 a.m. And there's one guy who at one point, like, he would say his dad was like shirtless or whatever. So, I mean, at the same time, there's always things like that. I mean,
Right.
yeah, because it's true. If you want to have a desk or something, I doubt you could put a desk like in a corner. I don't know. That's just one thing that could happen.
Because it's like I mean, everyone who is attending, everyone who's enrolled, right? They're making a big investment already. It's a big thing, right? That's their part in, they're at a stage in life where they're going to go to school and they're attending classes and so on, and it just seems like, it just seems like such a it seems like to be present and visible is really to their advantage to a great extent, and it seems like a shame to avoid that. But yeah, I think you can't just insist that everyone turns on their camera. That's like Big Brother or something. I mean, you also can't force people to attend class in person when we have normal school. I mean, if they don't want to come, they don't have to. So I guess, yeah.
I've heard some profs say that they'll be much more likely to write you a rec if your camera's on. They won't write you a rec if they can't see your face. And so that's a good incentive for students.
Oh, that's good. Yeah.
And I guess it falls within.
That's a sneaky way of getting people to do it. It's it means that you're kind of, yeah. In other words, they would, if they respond to that by actually turning on the video, then they're turning it on for the wrong reason. It's wrong. I mean, what it means is that if they're doing it for that means they should have turned it on already. I mean, there's no real reason for them not to turn it on. It's yeah, that's okay. Yeah, we're into time. So did anyone think about this simple question that I asked?
Can you repeat the question?
I'm going to ask, I'll repeat it later after someone answers. If anyone did think about it. Does anyone remember the question and maybe wants to state it again? As soon as the Zoom call finishes, out of mind, out of sight, out of mind. Anyone? So what about Zhang Han? Did you think about it? This question?
Sorry, what happened? I just joined. Oh, this question? No, I haven't.
Okay. So, oh, what's this? All right. So we have an object in 2 dimensions. We have a mirror. It gets reflected. So after the reflection through the first mirror, this becomes this. Then I have another mirror number 2, which reflects this into this. So after the first reflection, this thing is doing an orientation reversing isometry. In other words, the determinant of the linear transformation is negative, -1. And then the determinant of the linear transformation from here to here is also -1. So going from here to here, the composite of the two reflections is determinant +1, and it's a rotation. A rotation through a point which is the intersection of the two mirrors. So you may be have noticed this, that if you put two mirrors at right angles and look at them, then you see yourself, but you see yourself as others see you, right? In other words, you see a rotated, 180-degree rotated version of yourself. So if I ask the question, what is the angle of rotation from the initial to the final, what would you say?
Is it twice the angle between the mirrors?
Yes, why do you say that?
We're flipping the red one first, right?
Yeah.
So if you start with a point on the red line, then the first reflection does nothing. And then when you do the green reflection, that's equivalent to rotating by twice the angle. So if that point gets rotated by twice that angle, then every point must.
Yeah, that's one way to see it. The hint that I gave was that your mirrors, if they're at 90 degrees, give you 180-degree rotation. And indeed, the point is that if you think about building a rotation by using a pair of mirrors, then the angle between the mirrors gets doubled and you get this rotation. Okay, so this doubling of angle is going to be important for today, for this week. This week, we're talking about representations of SO3 and SU2. This doubling of angle is the key fact, which we need to keep in mind. So let's. So this week we're going to talk about rotate. So this idea will come back in a moment. Let me write it actually. So the answer is that the rotation angle is 2 theta, where theta is the angle between the mirrors M1 and M2. Okay, and the important thing about this is notice that if I ask you to write down the transformation, which is reflection through one mirror, right? If I say write down the reflection matrix for a single mirror, then what would you say? How do you give? Suppose that I have a basis E1, E2. I give you a mirror through the origin, and I ask you to write down the matrix of reflection. What's your answer?
Would it depend on whether the mirror is like a line, a normal line, or
that's a good question. So do you think that the reflection through this mirror or through this mirror, what would be the mirror? This is mirror 1. What would be the reflection through that mirror?
E2 would just be negative.
So as a matrix, what would be the matrix entries for reflection through mirror 1?
Is it always minus the identity? Like you're just negating all the coordinates when you do a reflection?
One second. I'm discussing with Gina. So if we reflect through M1, where does E1 get sent?
It would be also E1.
Where does E2 get sent?
to negative E2.
Okay. So what about if it was M2? What would be the, let's say M2 was, suppose M2 was at 45 degrees, say. Then what would be, where would E1 be sent?
I think it would just be, you would just switch E1 and E2.
So the matrix would be,
0, 1, 1, 0.
okay, so obviously the matrix depends upon the position of the mirror.
Mhm.
Okay. Now, we just finished saying that the rotation that is obtained from composition of two of these things is a rotation through double the angle between the mirrors. So what that shows is that it does not depend upon the individual position of the mirrors. It only depends upon the angle between them. So if you take two mirrors and orient them this way, right? If you take two mirrors at 45 degrees and look at it, you're going to see yourself rotated 180 degrees. And if you rotate that pair of mirrors, it will not change your apparent position. The will change your apparent position is if you change the angle between the mirrors. But if you change the mirrors like this, you're going to stay in the same place. Okay, so the rotation angle is 2 theta, where theta is the angle between the mirrors, and it of course, and as a result, it does not depend on the absolute angle of the mirror. It only depends on the relative angle between the mirrors. Okay, so right, and what happens if well, okay, so that's the answer to the first question. And the second question is that it doesn't depend on the position of the mirrors, only on the difference between the two. Okay, so let's start with representations of SU2 and SO3. Okay, so so just recall that for two-state systems, evolution and symmetries, they are in U2. So the Schrodinger propagator and the symmetries, they all have to be unitary transformations, and any unitary can be expressed as e to the I x or e to the I tx where x is self-adjoint. Now, if we think of self-adjoint, what does this mean? It means that the diagonal entries have to be real, and the off-diagonal entries have to be conjugate. So here's a basis for the real vector space of self-adjoint matrices, 2x2 matrices. So again, I said that the diagonal entries must be real. So that's 2 real dimensions. And then the off-diagonal entries have to be conjugate. So that's another 2 real dimensions. So in total, we have 4 real dimensions. One of them is just the unit matrix. That's obviously self-adjoint. And the other 3 are things you're familiar with already. They're the so-called Pauli spin matrices, because they are observables. And in the case of a spin 1/2 particle, which has 2 spin states, spin up and spin down, these are the observables of spin in the 3 spatial directions, x, y, and z axis. So you see this one, these are complex conjugate, these are complex conjugate, these are real. And then finally, sigma 3. So these are usually called the Pauli spin matrices. And this one is the one that is diagonalized. So we're writing these operators in a certain basis, and the basis is a basis of eigenvectors for sigma 3. So this corresponds to spin observable in the z-axis, and we're writing these observables in terms of the sometimes it would be called the up and the down basis, where sigma 3 times the up is just up, and sigma 3 times down has eigenvalue -1. Okay, and so the Pauli spin matrices are a basis for the self-adjoint matrices written in a basis for which the third one is is diagonalized. And the difference between the first and the last 3 is that we have a trace map. The trace map takes 2x2 matrices to the complex numbers, and the sigma 1, sigma 2, and sigma 3 form a basis for the self-adjoint matrices of trace 0. Okay, and the important thing about trace 0 is that if you take a self-adjoint matrix, so any self-adjoint matrix, so let me just explain as an aside the importance of trace x equals 0, okay, is as follows. So if x is self-adjoint, then x is similar to, it's diagonalizable. Okay, and so therefore the trace of x is the sum lambda I. And if I take e to the ix, sorry, so trace of x is the sum of the eigenvalues. And if I take e to the ix, this will be similar to e to the I lambda 1, e to the I lambda n. If I choose the basis for which x is diagonal, then it's very easy to exponentiate. And then the determinant of e to the ix is going to be equal to the product of e to the I, lambda k. Okay, and this is e to the I sum of lambda k, which is equal to e to the I trace of x. So we have an identity, a matrix identity, that the determinant of the exponential is the exponential of the trace. Okay, and so therefore, if the trace of x is equal to 0, this implies that the determinant of e to the ix, the determinant of this unitary matrix, is equal to 1. And therefore, that means that e to the ix is not just in un, it's in sun, the special unitary group. So, so what's really going on here is that we have all unitary matrices. This is a basis for all unitary matrices, but we've chosen the basis in such a way that these three form a basis for the special unitary, for the Lie algebra of the special unitary matrices. Okay, and this is just the extra direction in order to get the rest of the unitary matrices. So we basically have SU2 sitting inside, let me write it in a simple way. So U2 maybe just to summarize, the Lie algebra of U2 is all self-adjoint matrices. Excuse me, it's the skew adjoint, but we have this ability to multiply by I, so it's the set of X such that X conjugate transpose is equal to minus X, and the Lie algebra of SU2 is the same as above, but also such that the trace of X is 0. Okay, and so and so as you saw in the assignment, we can parameterize, or we can express for any T0, T1, T2, and T3 in R4, we can produce a unitary matrix by just using these as coefficients for the Pauli spin matrices. So I can do T0 sigma 0 plus T3 sigma 3, and this will be a family of unitary matrices parametrized by this 4 vector. Okay. Now this map from R4, so we get this map from R4 to the unitary group, and this map is surjective. It's not difficult to see why it's surjective, because you can take any unitary matrix and diagonalize it. And once you diagonalize it, you can express it as an exponential of some matrix. And then you can write that matrix in terms of the basis. So this is surjective, and this is easy to prove. by diagonalizing the unitary U. So if you take any unitary, you can find, you can write it as yeah, you can do as I said. So this is surjective, but it's not injective. That's the point that I want to make. Not injective. Okay, because we have a very simple simple fact, right? If you're exponentiating this matrix e to the for example, if you exponentiated e to the 2 pi I times this matrix, then of course this would just give you the identity. So if this 4 vector has certain integral multiples of 2 pi, you could end up with finding a self-adjoint matrix whose exponential is just the unitary matrix. And so this will have a kernel and the other thing is that this is not a group homomorphism. Okay, because it's not true that, you know, that, for example, because these matrices here, they don't commute. And so you cannot write this. This is not equal to, of course, not equal to e to the I t0 sigma 0, e to the I t1 sigma 1. You know, this is just not true because the sigmas don't commute. Okay, so this is just a parametrization of U2, but it is not a group homomorphism. So I shouldn't have said that it has a kernel. That kernel is not an applicable term in this case. Okay. Okay. Okay, so I just want to, I want to explain why this this way of thinking about unitary matrices is, or at least this basis, this way of thinking about, yeah, I want to explain how important this is. It's quite important in physics. So, so this means that any 3 vector, let's say B1, B2, B3 inside R3 gives rise, can be associated to an observable, to a self-adjoint operator. That is just B1 sigma 1 plus B2 sigma 2 plus B3 sigma 3, sometimes written as B dot sigma. Okay, so again, this may strike you initially as being a little strange because we're making a relationship between 3-dimensional space, real 3-dimensional space, and complex 2x2 matrices. So the complex 2x2 matrices, we're focusing on unitary ones. We're ignoring the simple part of the unitary. We're ignoring the multiples of the identity in the unitary. And we're focusing on the special unitary. So incidentally, maybe I should just make a comment in case people have not really seen these unitary. So just as a note, right, we have the unitary group, and inside there we have the special unitary group. So this is a subgroup, and it's by definition the kernel of a group homomorphism called the determinant, which goes to U1. Right, so any unitary 2x2 matrix, it has a determinant, which is a unit vector in the complex plane, U1. Okay, and the kernel of that group homomorphism, so this is a group, well, this diagram just means that this is the kernel of this map, the determinant map. And so there's a close relationship between the unitary group on the one hand and these two groups. So this is a quotient group by this subgroup. And so when you have a situation like that, you might wonder whether this group is actually a product of the two groups that appear, right? Is it really a product? So is there an opposite? Is there a group homomorphism going the other way, which we can use to express U2 as a product? So it turns out that there is a group homomorphism from here to here, which just takes e to the I theta and sends it to e to the I theta 1. So that's a 2x2 unitary matrix. Okay, but just because inside U2, just because we have a subgroup and we have another subgroup, okay, whose product gives all of U2, it doesn't necessarily mean that U2 is the Cartesian product of groups. There's this other notion which is called the semi-direct product of groups, okay? And that's exactly what's happening here. So it turns out that U2 is what's called a semi-direct product. And it looks like this. U1 is acting on the SU2 subgroup via a map phi, where phi is a map from U1 to automorphisms of SU2. And this automorphism is just conjugation by this element. So this phi of e to the I theta applied to a given matrix, let me call it U, would be e to the I theta 1, U, e to the minus I theta 1. So I just want to point out that that the unitary group has this decomposition, and you can do the same thing in any dimension, that UN can be expressed as a semi-direct product of U1 with SUN. Okay, but anyway, let's focus on SU2 for the moment. SU2 is SU2 is what's called a simple group, and we're going to focus on that, and we'll get to that later. But that's why I'm looking only at the 3 vector, and I'm only using sigma 1, 2, and 3, not sigma 0. So here we have a method for taking a 3 vector and converting it into a self-adjoint matrix. Okay, so what does that mean? That means that for every 3-dimensional vector, we get an observable for the qubit. Okay, and that's kind of interesting. That means that the qubit has something to do, or it can have something to do with three-dimensional space. Okay, what is the qubit? It could be just like a transistor. It could be like a switch that's on or off. It could be like the state of a quantum particle. But the fact that we have a two-state system, right? That two-state system could exist for any dimension space. Like we could be five-dimensional beings, and we would still use transistors. We would still have switches, right? There's, but on the other hand, what's happening here is that, integral to the two-state system is U2. Integral to U2 is SU2, and integral to SU2 is its Lie algebra, which is a three-dimensional Lie algebra. So 3 dimensions and the two-state system are intimately linked together. Okay, and it's for this reason that we know about electron spin. So the reason is that this observable, so if the two-state system is electron spin, which can be up or down, okay, then we can let B be the electromagnetic field, the magnetic field of electromagnetism. Okay, so in electromagnetism, there is this thing called the electric field, which is a vector in three-dimensional space, and there's the magnetic field, which is also a vector in three-dimensional space. And so because that's a 3D vector, I have the possibility of writing down this observable, okay, which I can measure on the two-state system, right? And I could use this, for example, as the Hamiltonian. So we could define H, the Hamiltonian, to be some number, which actually the way they break it up is like this, times B dot sigma. Okay, so mathematically speaking, okay, all I need to know is that there's something in physics which is described by a three-dimensional vector, B. And I need to know that there is a two-state system. You could even suppose that, maybe my electron is a two-state system, who knows? If it is a two-state system, then I can write down this Hamiltonian, okay? And the fact that I can write this down, right, the fact that this is well-defined, that gives me a theory, that defines me a quantum theory, right? Because I have my state space and I have my Hamiltonian. Okay, and what's the effect of this? Well, the two-state system is the same as it was before. It has two bases, up and down. The switch can be on or off, okay? But if I use this mathematical expression for the Hamiltonian, then what it means is that, so these are eigenstates of sigma 3, right? So this means that I'm going to have H applied to 1 will be times B3 times sigma 3 applied to 1. But we know that this is the +1 eigenspace of sigma 3s, because, so this is just 1. So this means that the eigenvalue, this is the eigenvalue of 1. So this is the energy of the state 1. On the other hand, if I take H applied to 0, I'm going to get GE over 4MC B3 times -1.
Why aren't we getting contributions from B2 and B1?
because I'm applying this to an eigenvector of sigma 3. And if you check, well, let me just take B3. You're right. Let me just take B to be B3. Suppose that the magnetic field is pointing in the Z direction. Thank you. So I'm going to arrange the magnetic field to be pointing up, and I'll use this as my Hamiltonian, and we're going to get these two energies for these two states, right? Now, so what this means is that the prediction of the theory, right, is that being up or being down will have two different energies. This will be, this will be of a lower energy than this. So there's going to be an energy gap between the two states. And so what you should expect is that now, so that means that according to this theory, if I turn my magnetic field stronger and stronger, the difference of energy between the two states of my switch will be affected. And so, for example, it will require energy to turn on that switch, and it will require exactly this much energy. Okay, so again, the fact that a two-dimensional quantum system, okay, has unitary group symmetries, and the fact that the special unitary group has a three-dimensional Lie algebra, which I can kind of, in this mathematical way, identify with any other three-dimensional object, right? What that means is that it becomes possible to allow any three-dimensional vector field to interact with my two-state system. So this is an interaction between any kind of three-dimensional thing. It could be the wind speed, okay, and my two-state system. It is possible for me to write down an interaction term. Now, it doesn't mean that it's a true interaction. It doesn't mean that the wind will actually change the spin of the electron, okay? But you can test it. You can test out, is this an interaction term which is actually there? Does the electron spin actually interact with the wind, or does it interact with the magnetic field, or does it interact with the electric field? And what they've found experimentally is that it actually does interact with the magnetic field exactly according to this constant of interaction, which is called a coupling constant. So this here has the name, this is the coupling constant, or sorry, coupling constant. And this is the interaction between B and sigma.
Professor?
Yeah.
Is it possible to determine whether or not such an interaction is well defined aside from by experimentation?
The fact that it's well defined is because I just wrote it down, right? So by experiment, you have to find out whether it's really there, whether the interaction actually is there. But the possible interaction, you know, what this is saying is that there is a possible interaction between any 3D vector and a two-state system. Whatever 3D vector field you find in nature, right? If it behaves like a three-dimensional vector, you can dot product it in with the Pauli spin matrices, and you can query nature as to whether that 3D vector field actually does interact with the quantum two-state system in question. Okay, so that's the concept that I wanted to explain. Okay, now it's really unfortunate how quickly time flies. But let me get to the main point. So so we have SU2, and we have the Lie algebra of SU2 is generated by sigma 1, sigma 2, and sigma 3. So it's the real span of sigma 1, sigma 2, sigma 3. Now let's look at SO3. The Lie algebra of SO3 is the set of 3 by 3 matrices such that X transpose is equal to minus X. These are the skew symmetric matrices. Okay, and the skew symmetric matrices look like this, A, B, C. So guess what? This is a three-dimensional, this thing which is called SO3. Is isomorphic to R3, and I'm going to choose a basis which looks like this. So the first basis element will be sigma 1, I'll call it, and that will be a 0, 0, 0, 0, 0, minus 1, 0, 1, 0. Sigma 2 will be 1 minus 1 with everything else 0. And sigma 3 will be 0 minus 1, 1, 0, 0, like this. Clearly, this is a basis for the skew symmetric 3 by 3 matrices. Okay, and this, the meaning of this is this will be infinitesimal rotation about the x-axis. And this one is about the y-axis, and this is about the z-axis. Okay, why do I say that? Well, the reason is because if I do e to the I t, I just want to make sure I want an I and not a minus I. That's fine. E to the I t sigma 1, right? That's oh, excuse me, sorry. This is already the Lie algebra. I don't need to put the I, sorry. These are not self-adjoint, they're skew-adjoint. So you could imagine, yeah, this is different since I'm in the real case. So if I exponentiate this matrix, what am I going to get? Well, it's kind of obvious. You're going to get cos t minus sine t, 0 sine t cos t. So you're going to get rotation by angle t about x-axis. Okay, so you see that these are the infinitesimal rotations about the x, y, and z-axis, and they don't commute, because you could, if you rotate about x and then y, or if you rotate y and x, you're going to get a different result. Okay, so so we have two Lie groups, SU2 and SO3. They have Lie algebras which are isomorphic because they're, well, they have Lie algebras which are isomorphic as vector spaces. They're just R3. Okay, these are 2 by 2 matrices, and these are 3 by 3 matrices. Okay, the reason is because the SU2 is acting on a 2-dimensional complex vector space, whereas SO3 is acting on a 3-dimensional real vector space. Okay. Now, the important thing, if you remember about Lie algebras, so Lie algebras are not just a vector space, but have a bracket. Actually, Lie algebras are not even algebras, because algebra has to be associative, and this is not. But anyway, Lie algebras have a bracket, okay? And if we compute the bracket of, I just want to set things up properly here. So I don't need, I can remember this quite easily. So if you take the Lie bracket of 2 skew-adjoint transformations, that will also be skew-adjoint. Okay, and so if you want to define the bracket, what you need to do is give it on its on the basis. So on the basis, what we have is that the bracket of sigma 1 and sigma 2 is sigma 3. And then there's cyclic permutations of this equation. So meaning that sigma 2 bracket sigma 3 is sigma 1, and sigma 3 bracket sigma 1 is sigma 2. So these are the relations, the defining the Lie bracket on SU2. Okay, and this can be verified just by commutation of matrices. This is just matrix commutator. Okay, on the other hand, okay, if we take sigma 1 and sigma 2 and take their Lie bracket or take their commutator, that's like infinitesimal rotation about x and then infinitesimal rotation by y, and then you check whether, if you do it in the opposite order, you get the same result. Okay, and if you check this, and you should do this computation, this is equal to sigma 3. And cyclic permutations also hold. So what this means is that although they look completely different, although one of them is 2x2 complex matrices and the other is 3x3 real matrices, as Lie algebras, they are identical. They're isomorphic. Okay. So, so this is, roughly speaking, this is the reason, this is like an important relationship between a two-state quantum system and 3D space. Okay, namely that the Lie algebra of rotations in three-dimensional space is the same as the Lie algebra of symmetries, special unitary symmetries of a two-state quantum system. Okay, so there's a there is a yeah. So I have to stop now, but on Friday we're going to explore this in detail. It turns out that that although the warning is that this does not mean that SU2 as a group is isomorphic to SO3. This is not true. It turns out that each of these groups is a kind of rotation. Okay, if you exponentiate sigma 1, that means that you're doing a symmetry of the two-state quantum system, which is a form of rotation. It's a unitary rotation. If you exponentiate sigma 1, that's doing a three-dimensional rotation of three-dimensional space. And it turns out that these there's a map from SU2 to SO3, but it has this feature that that it doubles angles. So if you rotate for a certain angle in the SU2 sense, that will be sent to a rotation in three-dimensional space, which rotates twice the angle. Okay, and this is the reason why I was talking about those mirrors. So the SU2 rotations, they are analogous to choosing mirrors which are differing by an angle theta, and they determine a rotation in three-dimensional space, but that rotation is not of the same angle. It has a doubling, and so we call this relationship a 2-to-1 covering. So there's a 2-to-1 map, 2-1 to SO3, and that's what we need to talk about on Friday. Okay, and this is This is really important because this implies that if you rotate a two-state system from, let's say, a state to 180 degrees, or like if you rotate half of a full angle in the SU2 sense, that means that you're going to be sending the basis to negative the basis. Okay, so if I rotate the states in the SU2 sense, okay, this will imply that we have a 2 pi rotation in SO3. So in other words, when you take an electron and you try to rotate it in three-dimensional space by 2 pi degrees, what you're really doing to it is only rotating halfway in terms of the two-state system. And so you do not return to the same electron state. In order to return to the same electron state, you need a three-dimensional rotation, which is double that. Namely, you need to rotate by 720 degrees. So if you take an electron and rotate it by 720, what that really means is that you're doing a 360-degree rotation in the SU2 sense. Okay, and then you'll get back to the identity. So this is the reason why if you take an electron and you rotate it 360 degrees, then it will be in the opposite state, and the two electrons will interfere. Yeah. So it will be like they'll be out of phase, completely out of phase, the two electrons. So that's a key difference between particles that have spin 1/2, is that when you rotate them by 360 degrees, they're not the same. They're minus, they're the state, they're in the opposite state, the state minus of itself. And that's true for neutrons, protons, all of those particles that have spin 1/2. They have an intimate relationship with three-dimensional space, but they are half angle. They're half angle in nature. They're like those mirrors. Notice that if you want to do a 360-degree rotation, the angle between the mirrors is exactly half of a full rotation. It's exactly pi. That's the thing. That means that you have two mirrors and you have to reflect and then reflect again, and you're going to be sent back to yourself, right? So if the angular separation between the mirrors is exactly pi, right, then you get an identity map on three-dimensional space, but the angle between the mirrors is still pi. It's not a zero it's not a zero angle or 360 degrees. Yeah, we'll continue on Friday, but if you have questions, I'll answer. Let me turn off the recording.